Good morning, class. I hope everyone is being healthy, going outside, being with friends, being physically active, maybe going to a concert, maybe running a marathon. Who knows? But today, we're going to make you mentally healthy with math. Hello, everyone. My name is Frank Nguyen.
And I am Brandon Tarasyuk.
Out of thin air, we've created this glorious function nicknamed r of x. It contains the expression x squared plus 2x minus 3 over x squared plus 4x plus 3. And as you can see here on this graph, it is very handsome. No flaws, just a perfect function.
Hello again. I'm now going to be going over the criteria for a function r of x. The first condition that our function must satisfy is that it should have the form f of x over g of x, both of which are polynomials. As you can see here, our f of x in this case is x squared plus 2x minus 3, and our g of x is x squared plus 4x plus 3. Since both are quadratic functions, criteria 1 is met.
The second criteria says that f of x and g of x must have two or three roots. Well, here, ladies and gentlemen, I will prove it. Here, I have separated these two functions. For both, if you factor them out, you'll be able to use these two incredibly simple algebra problems to solve for zero. When you solve, you should get that x equals negative 3 and x equals 1 for f of x, and x equals negative 3 and x equals negative 1 for g of x. Wow. Don't believe me? Well, here are some handsome graphs that prove me right. Unbelievable! I just proved that these two functions have two roots each.
Good morning, it's me again, and the third criteria our function must meet is that it should have at least one root. As you can see in our work, that root can be found by making the numerator equal to 0. In our case, x is equal to 1, where y is 0, so the root of r of x is at 1, comma 0.
The fourth criteria says r of x should have at least one vertical asymptote. Well, I'm pretty sure we did this project right, so I'm going to prove that my baby r of x does have one. If you rewrite the function and factor out the top and bottom, you can see that the function can easily cut out x plus 3. Now, what x value makes our function undefined? Did you say negative 1? Very good! Therefore, there's a vertical asymptote there. Don't believe me? Well, here's a graph to prove me right. This dotted line shows that the vertical asymptote at x equals negative 1. Wow.
Hey guys, it's me yet again, ready to go over the fifth criteria. The fifth criteria r of x must follow is that it should have a horizontal asymptote as its end behavior. Looking at the tables here, we can see that as x approaches infinity, or negative infinity, the y gets closer and closer to 1, but never reaches there. That must mean our function has a horizontal asymptote at y equals 1, and follows the fifth criteria.
And the sixth and final criteria, it has to have one removable discontinuity. Well, if you factor out my sweet baby r of x, you can see that there are two values that make the function undefined. X equals negative 1 and x equals negative 3. Well, you can cancel x equals negative 3 from the top and bottom, and thus it is a removable discontinuity. Here's a graph showing the whole, aka removable discontinuity.
Salutations everyone, it's me again, and I'm going to be showing you all our neat and detailed graph of r of x. As you can see here, our graph titled r of x is a reciprocal function that follows the x and y axis. The red dotted lines you see here are the vertical and horizontal asymptotes of the graph, and the hole you see at negative 3, 2 is the removable discontinuity in our function. Finally, the black dot on our graph is the root and x-intercept in our graph r of x.
Did you ask for the limits to this function for Christmas? Well, I'm Santa Claus and I'm here to deliver. Well, as x approaches infinity, r of x approaches 1. As x approaches negative infinity, r of x approaches 1. As x approaches negative 1 from the right, r of x approaches negative infinity. As x approaches negative 1 from the left, r of x approaches infinity. And you see this hole right here? We can't forget about this one. As x approaches negative 3 from both sides, r of x approaches 2.
Howdy, howdy, it's me again, eager to tell you about the first and second derivatives of r of x. We can find our first derivative by simplifying the function and canceling out the whole, and then applying the quotient rule. After all the work is done, we are left with our first derivative, which is 2 over x plus 1 squared. We can find the second derivative by using the same quotient rule like last time to find negative 4 over x plus 1 cubed.
You must be thinking, we analyzed this graph pretty hard, didn't we? Wrong. This handsome function always has more to give. Besides the limits, holes, and asymptotes that we talked about earlier, we also need to mention that there is an x-intercept at 1, 0 and a y-intercept at 0, negative 1. And because the first derivative of this function is always positive in its domain, the function is always increasing in this domain.
Hi, it's me, Brandon, again, with an MVT problem Frank and I crafted through our blood, sweat, and tears. Let's begin. Find all c that exist on the closed interval 0, 4, and the function r of x, which would satisfy the conclusion of the MVT. The first step in this problem is to check and declare the function is continuous and differentiable through the interval, which it is. We can find c by making the derivative r prime of c equal to the formula f of b minus f of a over b minus a, where b and a are the endpoints of the interval. After you plug in and do the work, we are left with plus or minus rad 5 minus 1. Since only one of those values can exist in the interval, our c is equal to roughly 1.24.
The intermediate value theorem. That's a lot to say. I'll call it IVT. Well, to prove that the IVT works, I'll choose the point 1, 0 on our function in the closed interval 0 to 4. By the way, the function is continuous on this interval, so IVT is going to work. We see that r at 0 equals negative 1 and r at 4 equals 0.6. Therefore, by IVT, there must be a value in the interval 0 to 4 that makes r of x equals 0.
Hey y'all, Brandon here. In this slide, I'm going to be going over the extreme value theorem. When we restrict our domain of r of x to an arbitrary closed interval of 0 to 6, we find that there are no critical points, so we must use the endpoints. This would be the case in any interval on our domain since our function is always increasing, which Frank told you 3 slides ago. In the interval 0 to 6, our absolute minimum is at x equals 0 for a value of negative 1, and our absolute maximum is at x equals 6 for a value of 0.714.
Now, we're going to find a tangent line at a point. Fenger said to use a convenient point, so what's the easiest point to use? 0, negative 1. So we're going to plug in 0 into r prime of x to find the slope of the tangent line. And we get 2. Now we are going to plug this slope into our beloved line formula, y equals mx plus b. Wow! And we get that b equals negative 1. Now we just slide that into the original tangent line equation to get y equals 2x minus 1.
Hello, it's, you guessed it, me again with the slide of the normal line. The normal line is quite simple to find since it is perpendicular to the tangent line. So all we have to do is change the slope that Frank found to its negative reciprocal and use the point slope form to confirm the equation of the line, giving us this graph with the black line being the tangent line and the red line being the normal line.
Wow, what a wonderful video to learn about calculus, am I right? If you love watching these kinds of videos, please smash the thumbs up button and leave a nice comment. But if you love seeing us making cool and fun videos together, please consider subscribing and we'll see you next time.
Peace.
Peace.